We have seen the three teams, optimization engineers, front-end developers, and data integrators working in parallel on the platform. We now have to integrate their work and show it to the end user to get feedback. This cycle, parallel development, integration, and feedback, will repeat several times during our project. The user feedback allows improving data quality, UI ergonomy, and optimization engine results. Doc applications are designed to support these iterations. When creating an application on the top of the dock, there are two main extension points that we need to integrate the user interface and the processing, which covers both the optimization engine and the data handling. The user interface is ready to use and does not require work at this stage. This is not the case with the processing code, which is in its library. To make it available in the application, we need to move it to an appropriate service. There are two ways to execute processing code, as back-end tasks or as worker tasks. The back-end tasks are meant to support short processing, for example, a small data check, a data import, or a snapshot export. They run in a shared service amongst all the users of the application. On the contrary, each worker task is running in a dedicated service on the optimization server. Those services are called worker services. You can have different worker services to support different worker tasks. You can also have multiple worker services to support the same worker task. To summarize, if multiple back-end tasks have to be processed at the same time, they will be run in separate threads into the back-end service. If multiple worker tasks have to be processed at the same time, they will be assigned to the available worker services or queued if not enough worker services are available. In our case, we will be using the worker services. We have to encapsulate the library code we have written for the engine and for the data checker into optimization server workers. This is done in two steps. We generate the two worker services using the framework generation feature, and we can call the library code inside each worker. Note that if we wanted to create back-end tasks instead of worker tasks, we would have followed a very similar process. We would have created two tasks in the back-end service, and we would have called the libraries inside these tasks. The framework generator comes with dedicated features to generate workers. There are three kinds of workers that can be created: one to call the default engine library, one to call the checker model library, and finally, a generic custom worker. Let's see how we generate these workers. Let's create our first worker. We are calling the framework generator with the new task option. We then select the checker worker amongst the three proposed choices. We have now generated a new service called checker worker. We can now create the second worker, the engine worker. We run again the same generator and we select the engine worker. We have now a second service called engine worker that contains all the files required to run our engine library and deploy the service. We have built the two new worker services. Note that we have made a few changes in the configurations to make sure that the Cplex libraries are accessible to the engine worker, and then used a Gradle command to build the services. Let's see how those workers will be executed. When the user starts one of those workers, the request is sent to the backend. The backend will call the data service to create an extract of the current scenario in a DOM collector format. This DOM collector will be serialized and sent to the worker by the optimization server. The worker will receive the collector work input. It will perform some processing using the collector API and data, and finally, it will return a modified DOM collector as output. This output will be sent back to the data service and synchronized with the scenario. Let's have a look at the generated code. The code comes into the capacity planning services, your project services. There is a worker folder that contains the two workers that we have just created. Let's first look at the checker worker. A new class called checker task has been created for you. It calls the checker we have defined earlier in this training in the capacity planning libraries model checker folder. As explained before, this checker task receives as parameter the collector. It creates a checker. It provides the collector as input and then retrieves the output collector and sends it back as a result. The principle we have just described is the same used in the engine task. In the generated engine worker service, we find an engine task class, which receives a collector as input, calls the execution method of your optimization engine, retrieves the output collector, and then sends it back as a result. At this stage, we haven't started the worker services yet. If we open the optimization server console and check the available task, we won't find any. We need to start our workers. We can use dedicated scripts. This will take a few seconds. As soon as the workers are available, they will register into the optimization server and become visible. Similarly, we start the checker worker, and we can see it in the optimization server. The UI, optimization engine, and data checker are now integrated into the platform. We are ready to show the application to the end users and get feedback. Let's assume we are sitting next to the end user, ready to start playing with the new application. The very first thing we might want to do is go into the Data Explorer and review the results of the checker. I'm opening the Issues table and run the checker task. Note that at this stage, the UI is connecting to the optimization server to detect which tasks are available. I will select the checker task and run it. Some notifications are displayed during the run, and as soon as it's over, I can see the results. In this example, we display the issues in a simple table. We can review them together with the business user. Running the engine is very similar. We will use the solution summary table to evaluate, together with the business user, the quality of the optimization results. I'm running the engine tasks now. As soon as the engine has completed the task, the scenario information is updated, and I can now see my solution summary, which tells me that my current planning takes 67 days. I can now move back to the solution dashboard. Let's now assume that my user wants to have something more dynamic to test different strategies. One of the strategies the user wants to try is to change the maximum headcount available for a given type of resource. How would the plan change if I only had 10 resources available for the painting activities instead of 15? How would the time span change? The first step will be to create a new dashboard that we will name What If. Since we want to play with the resource's headcount, we will add a widget displaying the resource capacity information. We now have a way for the user to change the headcount value per each resource type and test the impact on the schedule. For example, we can reduce the headcount for the resource M2 and run the optimization. Once the execution is over, we can move back to the solution dashboard and evaluate the new schedule. As expected, since we reduced the amount of resources, this has resulted in a solution with longer time to complete compared to the previous scenario. Now, our users would prefer having a more immediate way to check if the new schedule is viable or not before analyzing it in detail in the solution view. We can use the timespan KPI to quickly evaluate the schedule quality. This widget displays the time span in days. We can save. We can now have a quick way to evaluate the impact on the schedule of when changing the data. For example, let's increase the headcount for M2 and run the optimization again. The time span has reduced from 121 to 67 days. To make this more comfortable, I can add some shortcuts. For example, I can add a Run button to run my optimization. I will associate it with one of my tasks. And I can also add a navigation button, which allows me to move directly to another dashboard. Now, I can test the new widget immediately. I can run my schedule with a click. This will start the optimization solve. And I can click on the solution link to move to the solution dashboard. Another feature I can use is the default synchronization between different widgets. For example, when I click on a specific scheduled activity, I may want to see it highlighted in the Gantt chart. As you can see, the selection of the table is synchronized with the Gantt chart. I could also filter the Gantt chart instead of highlighting it. I can stop the synchronization and get back to the default view. When using what-if capabilities, we may create a lot of scenarios. Hence, it is useful to associate additional information with these new scenarios to indicate, for example, what kind of changes or hypotheses have been built into the scenario. We have dedicated a view that can be used for this. We call it Timeline. To open it, I will select a predefined widget, the Scenario Timeline. Now, I can add comments in this timeline associated with my scenario. This information will be stored in the scenario and will be available for all the users that have access to the scenarios. This is something very useful to collaborate with other users and to track what has been performed in any given scenario. We have given you an insight into how the different work produced by the different teams can be quickly integrated and shown to the business user. The platform supports quick interactions to validate the data, the UI, the optimization results, and the ergonomy of the whole application. This is really a key part of the development. We will be doing this assembly and integration steps many times during the whole project, and this is what we will guarantee at the end: acceptance from the end user, both on the quality of the solution and also on the ergonomy of the application.